and welcome to our continuing lectures on climate dynamics, climate variability and climate monitoring. In the previous class, we derived the zero-dimensional climate model and solutions to zero-dimensional climate models in terms of integration of the radiative forcing term. And we looked at one or two cases of various radiative forcing functions, like a constant radiative forcing and how that impacts the temperature perturbation over time, and a linearly increasing radiative forcing, which is similar to how the CO2 concentration is affecting radiative forcing today, and how that is affecting the rate of temperature increase with time in the climate system. Today we will discuss another little model where we are assuming that the radiative forcing increases linearly till a certain time t1 say, and then it achieves a constant value. So this will happen in case we are able to control our emissions of CO2 and CH4 and other greenhouse gases, and they reach an eventual new steady state concentration, so that the final radiative forcing due to these greenhouse gases becomes a constant again, say at the end of the 21st century. So this is called the ramp flat forcing, where we have a linear growth of RF with time, which eventually becomes steady after a certain specified time t1. Such a situation can approximate a case where CO2 concentration rises exponentially for a certain time and then stabilizes to a fixed mass fraction value as emissions decrease to zero. So this is the best case scenario we have for our case right now. So then the radiative forcing term will look like this. Up to a certain time between 0 to T1, it's equal to gamma T. Then beyond T1, it is a constant value which is equal to gamma T1. Remember, the functional relationship of the temperature perturbation with time is e to the power minus T by tau by C, RF T prime e to the power minus T prime by tau dt prime, this expression. So here we will integrate this in two parts. First from 0 to T1 where it is gamma T, and then for T greater than T1, so T1 to T, where it is equals to gamma into T1. Okay. So if we do that integration and then again do an integration by parts for the various components, the final expression of the temperature perturbation with time is gamma into tau by alpha. Remember, gamma is the slope of the radiative forcing term, tau is the relaxation time, alpha is the climate feedback parameter, equal to T by tau, which is our non-dimensional time, minus 1 plus e to the power minus T by tau. And this expression is between 0 to T1. Beyond T1, again we have gamma tau by alpha, T1 by T, minus, now we have a different formulation, minus e to the power minus T minus T1 by tau. Okay, so this new expression comes. This is the time, this is the T1, the time at which the radiative forcing becomes steady by the relaxation time, exponential negative of that, plus e to the power minus T by tau. This is for T greater than T1. Okay. When T is tending to infinity, so at very, very long times, then T minus T1 is much, much greater than tau. Okay, so this T minus T1 also tends to infinity, so this becomes e to the power minus infinity, so this becomes 0. Alright, this also becomes 0. Alright, so then T prime becomes gamma tau by alpha into T1 by tau, so gamma T1 by alpha, okay, or RF by alpha, because RF at that point is equals to gamma T1 at very long times. Okay, so this is again, if you remember, is the climate sensitivity term that we defined earlier. Remember, in the previous case, for the constant forcing case, we defined this climate sensitivity term RF1 by alpha. So here RF1 is your gamma T1. So this becomes RF1 by alpha, gamma T1 by alpha. So we are back to the climate sensitivity term. So T prime at very, very long times again becomes equal to the climate sensitivity function S. Okay. And this we would expect because again we have a constant radiative forcing and the initial difference does not make a impact on the final steady state value of the temperature perturbation. However, the growth rates are different, clearly. We have this function initially and this function in the middle. Okay, and finally it becomes RF1 by alpha. Alright. So, how does it look like? Okay, so it kind of depends on the value of this T1 by tau, your non-dimensional time fundamentally. So we have plotted the dimensional cases. All right. So this is T prime T and T, time and dimensional perturbation. This is your radiative forcing term, gamma T1 up to this point here. What is your case of the temperature term for two cases? In one case, the T1 by tau is much greater than 1. So this is the time at which the radiative forcing becomes constant. That time is much larger than the relaxation time tau. So the relaxation time tau is say 30 years say, and T1 is say 300 years. Okay. So for 300 years, the radiative forcing was increasing linearly, and at the 300th year, it kind of became constant. Okay. So in that case, you have T1 by tau is equal to 10, which is much greater than 1, for example. There, the temperature response reaches steady state just beyond T1. Okay, so the steady state value is reached quite close to the time at which the radiative forcing becomes a constant. Alright. The other case is where T1 by tau is of the order of 1. So if tau is 30 years, T1 is say 20 years or 40 years or 50 years or 60 years, like that. So of the order of 1, say 0.5 or 2, whatever. Alright. In that case, we see that the temperature continues to increase for a very long time even after the radiative forcing has become constant. That is, the greenhouse gases have stabilized. Okay, so this is kind of called the history effect, that even after we have stabilized the greenhouse gas concentrations, that is, we are no longer emitting any further CO2 and greenhouse gas concentrations, because we have emitted over a very short period of time, which is of the order of the feedback response time. So we have emitted say over a 90 years or something like that. There will still be a kind of pent up effect that will cause the temperature to continue to rise till it reaches the steady state level, which is RF1 by alpha. Okay. Eventually it will reach that, but it will take a long time, beyond at which we have stabilized the greenhouse gas concentration. Okay. So as again we see that initially the temperature response lags behind the radiative feedback response. So we have seen this effect before here. In the ramp forcing case, the temperature response lags behind the climate response, and then it linearizes, right? And then it kind of starts to level off, correct? So this difference becomes, if say for example, this difference is quite large in the initial cases and then kind of becomes stable, right? So this is what is happening here. Here, this difference is large, has kind of linearized by the time t equals to t1 has reached. So this has become linear. Here, the linearization has not happened. We are still in the kind of the slow rising case of the temperature response. Alright. So it kind of has to linearize and then level off. Alright. So as a result, you will have a long duration even beyond the stabilization of the greenhouse gas concentration, for which the temperature is going to continue to rise till it reaches the RF1 by alpha value. Okay. So it is kind of critical to understand the value of tau, understand when we are kind of stabilizing the greenhouse gas concentration in order to fully predict how much warming is still left after the greenhouse gas concentration has stabilized. Okay. So these are, we are going to more sophisticated models, but these very simple models kind of gives us a picture of what type of trends to expect for different cases. One final expression that we will do is an exponentially decaying pulse forcing. So what happens, suppose you have a large volcanic eruption or a large meteor strike, and a huge amount of aerosols get injected into the stratosphere. These aerosols will start to reflect sunlight and decrease the net incoming short wave radiation, and hence the net outgoing long wave outgoing radiation will increase. So we have a negative radiative forcing due to a net decrease in the incoming radiation at the tropopause level. Alright. So this has, because if you have inputting a lot of aerosols in a very quick amount of time, you have a rapid negative RF1, and this effect, as the aerosols then slowly again descend back onto the ground, this negative radiative forcing effect kind of decays back exponentially to 0. Okay. Where T0 is some constant based on the stabilization. So the aerosols slowly again kind of accumulate back onto the ground. They cannot stay in the atmosphere forever. So you have a slow decrease in this negative radiative forcing due to the aerosol caused increase in the reflection of short wave radiation. Alright. So radiative forcing is 0 for T less than 0. At T equal to 0, it becomes minus RF1, and then it slowly decays as minus RF1 e to the power minus T by T0. Okay. This is also a very interesting case because more recently there has been discussions of artificially injecting aerosols in the stratosphere to decrease the impact of warming. So instead of a volcano or meteor, we can use, say, aeroplanes or balloons to inject silicate particles in the stratosphere that are highly reflective and will reflect more of the short wave radiation. So the albedo will increase, and hence the net effective downward coming radiation will decrease, and hence you have a negative radiative force. So those cases also you have a pulse injection, human made or natural, which will cause a decrease in the radiative forcing, which will slowly decay back over time. Alright. So in this case, we can again plot the results and get the expressions. We will not do it here, but the basic idea we can write like this. The temperature profile will look like this. While the radiative forcing is exponentially decaying, the temperature will decrease, the temperature perturbation will reach a peak and then will slowly exponentially decrease as well. So temperature will rapidly decrease to a certain peak value and then slowly get back to its original steady state value over a certain period of time. Okay. So because the radiative forcing is decaying back to 0, temperature will go back to its original steady state level. And this is what happens in case of a large volcanic eruption or a meteor strike, that you will have a few years to a decade of cold temperatures because of the negative radiative forcing, and as the aerosols again go back down onto the Earth's surface, the temperature recovers once more. Okay. And it is proposed that an aerosol injection in the stratosphere will also do the same thing. It will give us a certain time over which the temperature is going to be lower and help us mitigate, though not completely remove, the impact of the positive radiative forcing due to CO2, methane, etc. So this kind of gives us a few cases of how the various radiative forcing functions can work together to have different types of temperature responses. Now we will discuss a little bit more complex models which does not just look at one greenhouse gas or one feedback parameter, but multiple parameters, all of which may have an impact on the overall flux. So in the previous simple models, we assumed that the net downward energy flux is only dependent on the temperature of the climate system and the concentration of the greenhouse gas. That is, the net downward flux is the incoming absorbed short wave radiation minus outgoing emitted long wave radiation at the tropopause level, which is a function of the temperature of the climate system and the one greenhouse gas concentration alone. Alright. Now this is not really true, as we know. in actuality, the climate system, in a climate system, the net downward energy flux will depend on three things. Firstly, the direct dependence on temperature, the temperature of the climate system itself. Then second, a set of temperature dependent climate variables which we define as V1T, V2T, going up to say VNT. Okay. So these are variables that depend on temperature and impact the net incoming flux. Examples of such variables include water vapor concentration. Very important, we will discuss this. So water vapor concentration in the atmosphere depends on the temperature of the climate system, because how much total water vapor is present increases exponentially as the temperature of the climate increases. We have seen this from the Clausius-Clapeyron relations that we discussed very early in our course. Concentration of clouds, again a very strongly temperature dependent parameter. Higher, warmer the oceans, greater is the rate of evaporation, greater is the amount of clouds. And we have not discussed cloud feedback in a lot of detail, and we will not discuss it today, but it's a very strong area of research of how the concentration of clouds as well as where the clouds are forming has an impact on the net incoming radiation. Albedo. So albedo is temperature dependent. If you increase the temperature, the snow cover decreases, so albedo increases, right? So albedo is also temperature dependent. Tropospheric lapse rate, of course a temperature dependent term. It also has a strong impact on the net incoming radiation and the radiation, because it impacts the temperature at which the atmospheric gases are emitting and absorbing the greenhouse radiation, the long wave and the short wave radiation, for example. Okay, so these are all variables that are dependent on temperature and also impact the net incoming radiation at the tropopause level. Okay, the third set is a set of climatic variables that do not depend on temperature. These are usually the concentration of the various gases and aerosols. The concentrations of various gases like CO2, methane, NOx, CFT, concentration of ozone, aerosol concentration, as well as solar insolation. The sun itself has its own cycle, so that also is a variable that needs to be taken into account in this set. So a set of variables that impact the net incoming radiation without being dependent on temperature of the system, a set of variables that are dependent on the temperature and impacts the net incoming radiation, and finally the temperature itself. Okay. So then the actual net incoming energy flux at the tropopause is F downward absorbed minus F upward is a function of temperature, the set of variables V1 to Vn which depend on temperature, and a set of variables x1 to xm that do not depend on temperature. Alright, and this helps us to define a generalized formulation of both the climate feedback parameter and the radiative forcing term. The climate feedback parameter, the complete expression then becomes minus del F del T, the gradient of this net incoming flux with temperature at the steady state greenhouse gas concentrations, minus summation I equals to 1 to n, that is over all these variables, del F del Vi into dVi dt, the gradient of the net incoming flux with the temperature determinant variables Vi into the gradient of these variables with temperature, summation of that. So this extra term as a summation for all of these variables are put into and becomes the actual climate feedback parameter we have to deal with in a more complicated model. And all of these derivatives are evaluated steady state value of temperature, VSS and XSS. So as we remember, del F del T at XSS, right? Similarly, del F del Vi at XSS. So these X values are being held constant. Okay. we can define the feedback parameter for the ith variable Vi as alpha I, as minus del f del Vi dvi dt, I going from 1 to n, and the direct temperature feedback value as alpha 0 minus del f del t. Okay. So this is minus del f del t, where all the other terms Vi's, Xi's are held constant. For alpha I, all the other terms are held constant. So V not equal to Vi is held constant. X, all the X terms are held constant. Okay. So the total feedback then becomes the direct temperature feedback alpha 0 plus summation over all the variables I to n which depend on temperature and also impact the incoming radiation. So alpha I, which is del f del Vi dvi dt. So this is the total feedback. So this expression is basically this expression. Okay. So here then we can model and evaluate the values of each of these alphas, alpha 0, alpha 1, alpha 2, alpha 3 for all the variables. Alpha 0 is the direct temperature feedback, alpha 1 may be the water vapor feedback, alpha 2 may be the cloud feedback, alpha 3 may be the radiation balance feedback, etc. Okay. The radiative forcing term can also be generalized in that format, that the total radiative forcing is summation over all the non-temperature dependent variables x1, x2, x3, x4 till xm. So summation j equals to 1 to m Rfj, where Rfj is del f del xj, the incoming radiation flux, the gradient of that with respect to the concentration of the mixing ratio of the greenhouse gas species xj into the perturbation of that species xj prime, the perturbation of concentration of that species xj prime. This one we only did for CO2, now we can do for CO2, methane, aerosol particles, NOx, CFCs, everything. Okay. All of that summation becomes the total radiative forcing for our climate system. Alright. We can still use the zero-dimensional energy balance model, C dt prime dt equals to alpha t prime equals to Rf t, just that the Rf becomes this expression here and alpha becomes this expression here. Alright. So we have just expanded the reach of Rf and alpha to contain all possible variables, temperature dependent or temperature independent, and we are using the zero-dimensional energy balance model. Okay. So we will stop here today. In the next class, we will try to evaluate alpha 0 and alpha 1, and then we will evaluate Rf for CO2. Okay. So that will give us a very good idea of how to do these analytical expressions and how to model them before we move on to the next section of our course. So thank you for listening and see you again in the next.